Today, we're going to continue looking at division, comparing between division with numbers and division with polynomials. And we're also going to remind ourselves of the relationship between multiplication and division. And we're also going to look at how improper fractions and mixed numbers mix in with all of this. So if you would recall, kind of a long time ago, we multiplied 23 by 17 and got 391. The best way to do this, of course, is to grab a calculating machine and to do 23 times 17. If someone asks how to do multiplication quickly, this is it. You use a machine to do it. But if we want to build a system where algebra is also arithmetic, we want to compare what we do if I multiply 2x plus 3 and the x plus 7. So just like over with 2x plus 3 and x plus 7, I multiply the 2x times the x. 2x times x is 2x squared. 23 times 17, we can do the same thing. We can take the 220 and multiply by the 10 and get 200. So this 2x squared is 2x times x, where this 200 is the 20 times the 10. Next, I need to multiply the 2x. So I multiplied the 2x by the x. I also need to multiply the 2x by the 7. So 2x times 7 is 14x. So that is the 2x times the 7. And just like we multiply the 20 by the 10 to lead off, I'll multiply the 20 by the 7. Every digit in one number gets multiplied by every digit in the other number. So 20 times the 7 is 140. So 200 plus the 140. So that is 20 times 7. Next, I need to go through and multiply the 3 by everything. So the next term, we'll get 3 times x is a 3x. So I'm going to multiply everything by 3. So the 3x is 3 times the x. And then we do the same thing over here in 23 times 17. I've multiplied everything in the 17 by the 20. Now I'm going to go through and multiply everything in the 17 by the 3. So 3 times 10 is 30. So that's 3 of the 10s. And then finally, we multiply the last. 3 times 7 is 21. And that 21 comes from the 3 times the 7. And we are doing the same thing over in our numbers example. I have to multiply the 3 by the 7. And that's 21. So I have the 240, the 200, the 140, the 30, and the 21. Those all add up to 391. They're all numbers, so we can just put them all together. Over in the polynomial end of things, there's only two like terms. I can't add x squareds and x's, they're not the same. But I can add the 14x and the 3x to get 17x. So I get 2x squared plus 17x plus 21. If I drop a 10 in for the x squared is 100, so this is going to be 200s. This is going to be 17 10s and 21 1s. So the 100 over here is going to push the 200 out to a 300, and the 20 and the 1s will push the 2 10s in the 21 will push the 7 10s left over in the 17x to 9. So 391 is also 200, 17 10s, and 21 1s. A lot of times when we're dealing with numbers, we don't always break them down as much as I did here. We don't always go 2 terms by 2 terms. But we might do, say, 10 times 23 and then 7 times 23. Or 20 times 17 and then 3 times 17. So we can break it down in a lot of different ways. So the good news is we have a lot of ways that we can consider what's going on in 23 times 17. We're trying to make things easy on ourselves, not more difficult on ourselves. but it might be that we take the 23, it might be that when we view 23 times 17, I might take 20 times 17 and add 3 times 17. That'll give me 23 17s. Here's a good way to break things down because 20 17s is easy to write. 2 times 17 is 2014 or 34, but it was 20, so put a 0. 3 17s is 3021, which is 51. And 340 and 51 is still 391. Note that all we're doing here is breaking the when we're doing 20 times 17, I still did the same thing. I still did 200 and 140. So if we don't recognize that 2 times 17 is 34 right away, we could break it into pieces, and then we're just back into this original problem up here. All we're doing is messing around with the distributive property. Because notice that that 340 is the 200 and the 140. And then the 51 is the 30 and the 21. Because I broke down 20 times the 17, here's 20 times the 10, and then I did 3 times the 17. That's the 30 and the 21. What we're trying to build is flexibility, not speed. Once again, if you're doing this by hand, you are going to be slower than the calculator. We're not going for speed, we're going for flexibility. Once again, the reason that I do this is that too often I have students that are super proficient in this and everybody's cool with it. They set it up in that weird vertical way where they carry the, where they do 3 times 7. So they put the 1 down the bottom and they carry the 3, which is really weird, but that's what you were trained with. But then if I ask them to multiply 2x plus 3 times x plus 7, if I ask for 23 times 17 in polynomial form, all of a sudden, it's not, it just doesn't, we don't see them as the same thing. So I care not about speed because no hand method is going to beat the speed of the calculator. And second of all, the calculator isn't even going to be faster than the person that just does this quickly. Some people are just good at this and they're just going to be able to do things quickly. Any questions? Note that this same thing down here is part of building up this multiplication. I just did 20 times the 17, so I could write this 2x plus 3 times the x plus 7. I could write that as 2x times the x plus 7. And then I can just add the 3 times the x plus 7. This gives me the same 4 terms that we had before. 2x times x is 2x squared. 2x times 7 is 14x. 3 times x is 3x. And 3 times 7 is 21. Same 4 terms that we had when we did FOIL. We want to think about multiplication as being the same operation with numbers and with polynomials, because that's why we call it multiplication, because it's the same operation. We also want to recognize how division is connected to multiplication. If we know that 23 times 17 is 391, then almost for free, if we ask what 391, if we want to take 391 and divide it by 23 is, we'll get 17. So in the polynomial land, the same is true. If I take 2x squared plus 17x plus 21, and divide by 2x plus 3, we should get the x plus 7. Now we can do this in terms of long division. This is what should happen. This is what we know. If we already know that 23 times 17 is 391, then we also know that 391 over 23 is 17. So we should get 17 if we do the division on 23 from 391. So if I tried 23 and divide that into 391. Once again, we want to think about how many times we could subtract 23 from 391 without going negative. And we start in the tens place. How many times can we subtract 23 from 39 or 390 without going negative? And we can do that 10 times. So this 1 represents 10, and so we're going to subtract 10 copies of 23. We usually just write 23, but what we should write if we want to understand what's going on is not 1 times 23 is 23, but just stick it under the 39. This 1 is in the tens place, so this 23 down here is actually 230. This 1 is actually a 10. So I'm not doing 1 times 23, I'm doing 10 times 23. So here are 10 copies. So this is 10 times 23, not 1 times 23. And then we subtract because we're doing division, and division is just repeated subtraction. 391 minus 23 is 161. And then we're just going to continue subtracting. We've subtracted 10 23s, and now we're going to see how many more we can subtract. Can't subtract 10 more, otherwise we would have put a 20 up on top. So 10 23s is 230. So 9 23s is still going to be too much. So we just think 9 23s. If I take 23 off of this, 9 23s is 207. 8 23s. That's still going to be too much. 207 minus 100 minus 20 is 187 minus 3. So 207 subtract 187 minus 3 is 184. That's still too much. Let's subtract another one. 7 times 23. So 18 minus 180 minus 20 is 160, and then 4 minus 3 is 1. So we can apparently take 7 more tens. So now we could really see that that 1 was actually a 10. So let's take 7 more 23s. 7 times 23 is 161. And we subtract and come up with 0 remainder. So we get 17 and 0 23s. We do the same process if we divide in polynomials. We're trying to decide how many times, if I want to divide 2x plus 3, if I want to divide 2x squared plus 17x plus 21 by 2x plus 3, I want to know how many times I could subtract 2x plus 3 from 2x squared plus 17x plus 21 without going negative. Now things are a little bit weird. I got to adjust a little bit. What I want to do is I want to get rid of this 2x squared. So how many times, if I want to subtract 2x plus 3 from the 2x squared, I have to multiply by an x to make that happen. So now x times the 2x is 2x squared, because when I subtract, I want that to go away. And then x times the 3 is plus 3x. Now I'm going to subtract. (2x squared minus 2x squared goes away. That was the plan. That's the whole reason that we put up the x up here, is to get rid of this x squared term. And then 17x minus 3x is 14x. So right now my bad habits are showing through. I subtract the 2x and the 3x just from these first two terms, but I'm subtracting the 2x and the 3x from this whole polynomial. The 21 doesn't follow down. It's just 21 minus 0 is 21. But this 2x squared plus 3x is just x times the 2x plus 3. So we just repeat the process. I want to subtract 2x from 14x, so I can do that 7 times. 7 times the 2x is 14x. And 7 times the 3 is 21. And so when we subtract, we get no remainder, just like we expected. Also, look at the 4 quantities that we put in green. We have the 2x squared and the 3x. That's the 2x squared and the 3x from the multiplication. We also have the 14x and the 21. That's the same 14x and the same 21 that we had when we were doing multiplication. It didn't quite show up in the multiplication or the division when we were doing with numbers. But here we have 230 was our first subtraction, which is 2x squareds and a 3x. The 230 is 20 tens and 3 tens. It's the 20 tens here and the 3 tens here. The 161 is the other two. It's the 27s and the 3 sevens. Notice that it's 23 times 7. It's 27s plus 3 sevens is the 161. So the 230 corresponds to 2x squared plus 3x. The 161 corresponds to 14x plus 21. We're just doing this multiplication in reverse. That should make sense because multiplication and division are inverse operations. All super connected up. We don't just get one division. If 391 divided by 23 is 17, then for free, we get 391 divided by 17 is equal to 23. So that would also mean in terms of polynomials that 2x squared plus 17x plus 21 divided by x plus 7 should be 2x plus 3. Let's see that happen in numbers in both cases. So let's divide 17 into 391. So we start off by saying, how many times can we subtract 17 from 391? And we start by just looking at the tens and the hundreds. How many times can we subtract 17 from 39? And we can do that twice. That's what that 2 means. But that 2 is actually a 20. Because we're not subtracting 17 from 39 twice, we're subtracting 17 from 390 20 times. And so 2 times 17 is 34, but what we're really doing is 20 times 17 is 340. And we're subtracting because this is division, which is repeated subtraction. So 39 minus 34 is 5, and then there's a 1 left, the 1. The 1 doesn't bring down, it's 1 minus 0 is 1. And then we need to subtract 17 from 51, and we can do that 3 times. 3 times 17 is 51, so up here goes a 3. 3 17s is 51. And when we subtract 51 from 51, we get 0. So we get no remainder. 391 over 17 is 23. Notice that we subtracted a 340 and a 351 because we're subtracting groups of 17. The 340 is made up of the 200 and the 140. that's the 340, and the 30 and the 21, that's the 51 that shows up in the division. These aren't completely disconnected. They're just grouped differently. Before we had the 230 because we were focused on the 10. But here we have the 200 and the 140 because we're focused on the 20. Let's switch over to polynomials and see all the same things happen. If I take x plus 7, I want to divide x plus 7 into 2x squared plus 17x plus 21. We're asking the same questions. How many times can I subtract x from 2x squared? And that's going to be 2x times. I need an x to make like terms, and I need 2 to make the 2 cancel out. 2x times x is 2x squared. 2x times 7 is 14x. The same 200 and 140 that we had before. Oh, excuse me, the same 2x squared and 14x that we had before in the multiplication. Now we're subtracting this from the whole polynomial. The 21 is not just going to be brought down. We're going to say 21 minus 0 is 21. 2x squared minus 2x squared is 0, x squared, so that's what we wanted. 17x minus 14x is the 3x. 21 minus nothing is 21. Now I need to subtract x from 3x to cancel that out, and I can do that 3 times. So I'll put a plus 3 up here to indicate I can subtract x from 3x 3 times. So 3 times x is 3x. 3 times 7 is 21, and we get no remainder, just like we expected. Look at the 4 terms that showed up. We got 2x squared minus 14x. We got 3x and 21. It's the same 4 terms that we had when we multiplied those polynomials, the 2x squared and the 14x and the 3x and the 21. They just showed up in different pairs depending on what we were dividing by. When we divided by the 2x minus 3, we got rid of the, we focused on the x. And so we had the 2x squared and the 3x together in one line. And then the next line had the 14x and the 21. But when we divided by x minus 7, the first term was a 2x, so it gave us the 2x squared and the 14x, the 2 terms out of the 4 that involved the 2x. I know I do these problems a lot because what's important to me is not that we can do long division, but what's important is that we understand how long division works, so that when we're working with polynomials, we just adapt to the new form of number that we're looking at. And once again, I'm going to completely ignore any arguments about what's faster, because what's faster is step 1, use a calculator, and what's faster than that is step 2, just get faster. Someone's always going to be faster than you. Someone's going to say, well, you divide these numbers and I'll do it in my head and I'll be faster than you on a calculator, because speed is not the point. Understanding is the point. Any questions? So the other reason that I keep doing this over and over and over again so you get sick of it is that when you're sick of it, it's because you're thinking, yeah, Leach, we totally got this. We're good. And I'm like, oh, great, let's do another example. And I go, do we still have to do this? And I'm like, oh, yeah. Because professional basketball players still go out there and work on shooting free throws. Professional baseball players still go out there and work on picking up ground balls and throwing over to first base. You want to be better at a thing, you got to practice it. Any questions? Great. Now, In these two examples, everything worked out nice and clean. So 391 divided by 23 is 17 with nothing left over. What if we are going to get a remainder? Let's look at an example with a remainder. Let's look at an example with a remainder. Let's suppose that instead of 391 over 23, so we know that 391 divided by 23 is equal to 17. That's facts that we have in evidence. Similarly, we know that 2x squared and 17x and 21 over 2x plus 3 is x plus 7. So we know that when we do the division, 391 divided by 23, we get 17, no remainder, no fraction parts. So I'm going to change my 391, and I'm just going to add 5. So I'm going to do 391 plus 5. I'm going to put 396 divided by 23. So what if it's something that we know is not going to work? 396 divided by 23. Let's see what happens in the division. So we should predict a little bit about what's going to happen. We're going to subtract 23 from 396 17 times, and there will be 5 left over. Because we know that 391 over 23 is 17, because we already know this, we know we can subtract 323 from 396 17 times. So the thinking is that since 391 over 23 is 17, we can subtract 23 from 396 17 times, and there will be 5 left over. Oops. The 5 remainder is the 5 left over after we subtract 23 from 17. 23 from 391, 23 from 396 17 times. Sometimes this process gets buried, or this recognition gets buried in the process. Let's do the division and see what happens. So let's suppose that we have 23, and we're dividing that into 396 this time. So we want to subtract 23 from 396. We know we can do that at least 10 times. So I'm going to put the 1 up here. That 1 represents a 10, and we're going to subtract 23 from 396 10 times. So 10 times 23 is 230, and we're subtracting. 396 minus 230 is 166 this time. Last time we had 161, now we have 5 more, because all the subtraction took place in the hundreds and the tens column, so the ones are still just say, hey, I still got this extra 5. If we think back to what we already have in evidence, 7 23s is 161, 8 23s is 184. We don't have a full set of 23s, so we can only subtract 7 without going negative. 7 23s is 161. And when we subtract, there are 5 left over. Now we have, this is the remainder, because if we try to subtract any more 23s, if I try to subtract 18 23s, I'm going to end up going negative. So the 5 left over is going to be the fraction of 23 that we have left over. So 396 over 23, I can do this 17 whole times. And there are 5 23s left over. And so the way we say that is 17 is the whole number part, and there are 5 23s left over. There are 5 left over. The same thing should happen. We should see the same kind of stuff happening if we divide a 2x squared and the 2x. So all I did was I just added 5 to the 391 to make a 396. So let's just take 2x squared plus 17x plus 26. I'm just going to add 5, and we're going to see what happens. So I make the 2x plus 3, and I divide that into my 2x squared, 17x plus 26. Same thinking that we had before. I want to subtract the 2x from the 2x squared, so I need to multiply by x to make them like terms, and then the 2's are working themselves out. X times the 2x is 2x squared. X times the 3 is plus 3x. And I'm going to subtract these terms from the whole polynomial. 2x squared minus 2x squared is no x squared. That's what we wanted. 17x minus 3x is 14x. 26 minus 0 is 26. Same thinking, same process, just altered it a little bit. Next, I need to subtract the 2x from the 14, and 14x, and I can do that 7 times. 7 times 2x is 14x. 7 times 3 is a 21. Notice that in green, we still have the same 4 terms from our multiplication. 2x plus 3 times x plus 7 is going to have a 2x squared plus 3x plus 14x plus 21. It's the same 4 terms from the multiplication. But this time, we're subtracting from 26, and there are 5 left over. So when I write my answer and I divide these two polynomials, the whole number part, or the whole polynomial part, is an x plus 7. But there are 5 left over. So I have to separate the polynomial. I can't just write a fraction, 17 and the 5/23. Our standard for mixed numbers is just to smash the two together. But what this means is 17 plus 5 over 23. So I'm going to put plus 5 over the 2x plus 3. We still had 5 left over because all I did was take 5 and add 5 to the numerator. Now, the reason that I like to go over division is that we can always use division. One of the things that we want to learn that we usually learn in algebra class is to factor a polynomial. The problem with learning to factor polynomials, I have no problem with learning to factor polynomials, so I'll just state that. I think it's a very niche thing to be able to do. And what it does is it sets us up with this false expectation that most polynomials are factorable, but that's just not the case. The reason we get the idea that most polynomials are factorable is that teachers want students to practice factoring, and so they give them big piles of factorable polynomials to practice their factoring skills on. When really, if you want one thing to do, just learn to divide. Learn to figure out what you should expect would show up as a factor. What could show up as a factor based on the polynomials that you're looking at. So if we put these things together, rather than just putting factoring in its own little silo and not connecting it to things like multiplying and dividing polynomials, then we're going to get better at factoring, which is, for some reason, a skill that we want everybody to have. I promise you, once you get out of your algebra class, you won't have to factor polynomials anymore. I suppose if you take calculus, which you all should do because it's cool, when you take calculus, I'm going to phrase it that way. When you take calculus, you're going to have to factor some polynomials. But unless your teacher's being unreasonable, they're going to be quick ones to factor. Any questions? Comments? Big thoughts? I guess the big thing that we want to recognize is that when we're trying to do this division, note how much is stored up in the 2x squared and the 17x and then 2x plus 3. This constant at the end is just going to tell us about the remainder. So if I modify this problem even further, if I look at, say, 2x squared, here's what I want us to be able to recognize. In a math class, the whole point should be to get to the point where you understand what's going on so that you don't have to do the process. You don't want to have to write out this process. It's not about what you're writing, it's about what you understand. So if I take this x squared plus 17x, 2x squared plus 17x plus 26 divided by 2x plus 3 and then modify it to 2x squared plus 17x, let's say, plus 16, and divide by the 2x plus 3, especially if I give you this problem after these two problems. We should recognize that the things that we're going to want are the 2x squared, the 3x, the 14x, and the 21. And so that when we divide, we're still going to get an x plus 7. But instead of the 16, or instead of 26, which was 5 above the 21, which is in the middle, I have 16, which is 5 below the 21. So 2x squared plus 17x plus 16 is going to be x plus 7, but not plus 5, but minus 5 over 2x plus 3. If we've already divided the 2x squared plus 17x plus some constant by a 2x plus 3 and come up with x plus 7 plus some remainder, then if I subtract and make the remainder negative, we shouldn't be thrown by that. Moreover, if I give you 2x squared, if we paid attention to what's going on and we understand what's going on, not can do the division, but understand what's going on, if I drop the x plus 7 down here, especially if I do it right after this problem, should be no problem. If I instead now divide by 17 instead of 23, then the 23 will show up here, and we'll still be off by 5. Oops, although it won't be x plus 3, it'll be an x plus 7. Moreover, everything still fits together because one of the things that we know is that if I want to take a mixed number, let's say 3 and 2/5, and I want to turn it into an improper fraction, I know I do 3 times a 5, or I do 5 times 3. I know it's the same thing, but I do 5 times 3 and then I add the 2. 3 times 5 is 15 plus 2 is 17 over 5. So what that means is that 17 and 5 23s is going to be 23 times 17 plus 5. Notice that if I multiply x plus 7 times 2x plus 3, I get 2x squared plus 17x plus 21. Then if I subtract 5, I'll be at plus 16. So if I take, let's see, I have been writing here, x plus 7 times 2x plus 3. So if I take x plus 7 and multiply by the 2x plus 3, and then subtract the 5, this will be the improper fraction over the x plus 7. X plus 7 times 2x plus 3 we know is 2x squared plus 17x plus 21. And then we subtract 5, and that gives us the 16. Algebra is not new, it's just arithmetic. All the things that you know about arithmetic are things that you just have to modify so to become things that you know about algebra. We're not doing new stuff. We're doing the old stuff. We're reinforcing old stuff and applying the old stuff to new things. All right, that's going to do it for today. That's going to do it for this week. Next week, we want to talk about quadratic functions in a little bit more detail, because I kind of trashed the quadratic formula, and that's sometimes the big finish to your algebra classes. And then we got to learn how to solve for some exponents, and then we'll have a nice complete picture of what algebra is like. That's going to do it for today. That's going to do it for this week. Everybody have a nice weekend, and I'll see you all on Monday, and thanks for playing.